Good evening, everyone. My name is Maneesha. I work as Associate Professor at South Dakota State University. Um, and I'm going to present about novel process and ingredients in dairy. These are some of my research insights over the past years of my research career. So just to give you an outline of my trajectory so far, so that to give you an understanding for all the students who want to pursue higher education at US or rather in other countries. I did my bachelor's in dairy science and technology from Kerala University, did some time as technical superintendent at Products Dairy in Kerala. And then I did my master's at South Dakota State University and a PhD at University of Tennessee. Then I went on to do postdoctoral research at Pennsylvania State University and did another postdoctoral position at Irish Food and Agriculture Research Institute, and then did some work in the industry as R&D scientist at Glanbia Consumer Foods, also in Ireland, before moving to New Zealand as a faculty at Lincoln University. Eventually, I moved to South Dakota State University as associate professor in dairy manufacturing. So this has been my trajectory, and I have been around the world in probably 12 years or more. So it has been a good experience. And I worked with a number of academic institutions as well as industry. So I've worked in an interface of academia and industry, and this gives an idea of all the institutions I've worked in research and for processing in terms of academia as well as industry. When we talk about the dairy sector, as a broad overview, one thing that is constant in the dairy sector is change. And some of the emerging aspects or emerging trends in the dairy area has been cleaner labels, demand for healthy and nutritious food. Of course, there's increase in milk production all around the world, and that creates diverse product lines and the need for value addition. And also, the changes in environmental impact has also affected the way we look at the increasing herd sizes or mega farms in many countries. So overall, this creates a need for new process, which needs to be optimized and new ingredients to find applications for, and also to find new markets. So my work has been in the area of dairy processing and engineering. And some of the topics that today I'm going to discuss here is from my research in different institutions. So I won't go through it now. We'll go through it one by one. So first, let's talk about valorization from farm level, which was part of my master's work at South Dakota State University. So the idea was to enhance conjugated linoleic acid in cheddar cheese by dietary manipulation and also adding a special starter culture. So we fed fish oil, about 0.75% dry matter, to cattle, and the milk was collected from the cattle, and this milk was used for making cheese by adding a starter culture that can produce conjugated linoleic acid. And there are a number of health benefits of conjugated linoleic acid, and that's the reason why we wanted to enhance the quantity of conjugated linoleic acid in cheddar cheese. And from this study, we were able to increase this amount of conjugated linoleic acid in cheddar cheese up to 2.4 times compared to the control, which did not have the dietary manipulated milk or the starter culture. So another, moving on from the farm level to the product level and the processing technologies, and the number of novel processing technologies and ingredients that I've worked with. Let's start by talking about high pressure treatments, which I have worked with during my PhD as well as one of my postdocs. Just to give an idea, an overview of different kinds of high pressure treatments, there's a high hydrostatic pressure treatment as well as a high pressure homogenization. These are two different kinds of processes where the high hydrostatic pressure happens in a static chamber. So it's not a continuous process, and the pressures can go up to 1,000 megapascal. While the high pressure homogenization, as I said, is a continuous process. And because of that, there are a number of forces acting within the system, and it can go only up to a pressure of about 400 megapascal. And some of the forces acting are shear stress, turbulent flow, heat can also be generated. There's, of course, a high hydrostatic pressure, but in turn, there's also cavitation and impingement as well. So that brings me to the specific kind of high pressure homogenization technique that I used to process milk, which is a ultra high pressure homogenization, because we went beyond the 400 megapascal normally used for high pressure homogenization to about 500 megapascal, which is the maximum that can be attained for a high pressure homogenization pressures. This is not really commercially applied yet, this technology. So what we did is we had a water jet, which is basically high pressure water used to cut concrete and other hard materials, and we adapted that to process milk. And we observed that the foaming ability of the high pressure jet processed milk was higher as the pressure increases. You can see in the picture, the foam is much more stable, and also larger quantity in the 500 megapascal compared to the 300 megapascal processed milk. So we looked at the particle size. As you can see on the right-hand side is a graph of the mean particle size of the casein micelles in these different kinds of milk processed at different pressures. And we found out the structure of the casein micelles changed considerably, and the dye binding capability also changed. As you can see, the type of structure has changed in the images within the graph, and also the particle size has increased considerably as the pressure increases as well. So we hypothesized that as the pressure increases, the porous open structure, when it reaches about 100 megapascal, it gets slightly disrupted, the micelles. But as the pressure increases, it leads to compaction and aggregation, and also eventually at 500 megapascal, there is further redispersion of the micelles. So we got new kinds of particles, which are basically controlled aggregated particles. So these create a lot of possibilities of novel processing technologies for making new ingredients as well. So some examples of dairy ingredients that can be formed by modifying different properties like foaming agents and stabilizers can be obtained by controlled acidification or by partial aggregation. So one example that I already gave is high pressure and for partial aggregation, and also another technology that can be used is the ultrasound technology for partial aggregation as well. Just to give you some ideas in terms of how some of the properties change with controlled acidification. As you can see, the foam overrun and stability was higher as the pH was reduced to 5.5 compared to the normal pH of milk of about 6.6 or 6.7. And if you look at the partial aggregates, the foam stability using two methods, shaking and sparging, the foam stability increased considerably as the aggregate concentration increased as well. So this gives an idea about how we can make modified casein powders with new functional properties that can be used as ingredients in different kinds of food products and applications. So some applications include coffee, foamed beverages, ice creams, and mousses. Okay, talking about another novel processing technology, which is a nanobubble technology, which is a technology that we used at Lincoln University, and I am continuing the work with nanobubble technologies in the effluent treatment and dairy processing as well. What we observed, so nanobubbles are basically, as the name suggests, small bubbles of different kinds of gases. We use nitrogen-based gas, and what we use is we make these bubbles in our water, and these bubbles have very specific characteristics or properties. So these are nano-sized bubbles. So what we found out was that as the amount of nitrogen nanobubbles increased, the dissolved oxygen in the water decreased over time. That means that the nitrogen nanobubbles, or the nitrogen, is replacing the dissolved oxygen in the water. So this is an indirect way of figuring out how much nanobubbles are present in the water. And also we found that the nanobubble water had a higher electrical conductivity compared to the RO water alone, as indicated in this graph here. So this picture gives an idea about what are the characteristics of nanobubbles compared to microbubbles or macrobubbles. So nanobubbles, they have Brownian motion, and they're very stable and can stay stable for quite a long time, even up to a few days. And because of the smaller size, they have increased surface area and hydrophobicity as well. So that means that there are lots of applications for nanobubbles. So it has been studied for application for improving crop yield in agricultural industry, in textile industry for increasing the dye efficiency, in the medical science for targeted drug delivery, and also in the marine industry to improve the shelf life of fish. But my interest was to figure out the interactions of nanobubbles with milk proteins, which could be potential application for the dairy industry as well. And the work is still ongoing. So from NOAA processing technologies, we move on to talk about other kinds of value addition for solutions in the dairy industry. For example, how can we add value to milk fat? Because milk fat has been utilized as it is for all kinds of products like whole milk powder, as a part of whole milk powder, cheddar cheese, butter, cream, and ghee, and hydrous milk fat, and so on. So the milk fat component, because of its high value, has not been invested in as a new ingredient or modified to get different kinds of properties like the proteins, which have been fractionated and sold as different kinds of products throughout the world. So there's lots of avenues for utilization of milk fat, especially since the world milk production is increasing quite steeply over the years and will be about 1,000 million tons in 2025. That means that the amount of milk fat that will be available at that time will be 35 million tons or so, based on 3.5% fat content in that milk. So that means we'll have more and more milk fat available that needs to be utilized or added in value. And there are many ways of doing that. And some of the ways that I suggest in my past work at Teagasc in Ireland was supercritical fluid extraction. So basically we can extract specific components out of the milk fat that will enable us to utilize the specific properties of these fatty acids or triglycerides. Or other lipid fractions to be utilized as specific ingredients. Another technology is ultrasound spectroscopy, which can be utilized to study the crystallization properties of milk fat, which can be modified and studied in line to get different kinds of softer fat spreads and butters and so on that can stay soft at room temperature. Dry fractionation is an age-old technology that's also used for fractionation of different kinds of oils and fats, which can also be used to produce different melting fats, which are called olein, which is the liquid fat, portion and also a solid fat portion as well, which can be utilized for different kinds of applications and different kinds of food products, including the bakery industry. So there's a lot of opportunity for fractionation and value addition of milk fat, which hasn't been explored too much yet. So moving on to other dairy ingredients and some novel ingredients for the dairy industry. So a novel ingredient that we developed at Lincoln University for dairy application is a gelling agent. And this gelling agent was made with disodium guanylate in combination with organic acid. And disodium guanylate is GRAS, or generally recommended as safe for consumption in or application in food industry. So it is a widespread ingredient used in the food industry in China and so on. It's what we figured out is that as we looked at the YX is the yogurts that were incorporated with the disodium guanylate gels. So basically these gels can form, the disodium guanylate can react with the lactic acid in the yogurt made by the lactic acid bacteria, and then the viscosity can increase over time. So over time, it will get more and more firmer. And also another aspect that we observed is that the viscosity at low shear rates were very similar to normal yogurts, but at higher shear rates, like what we see in the viscosity of the disodium guanylate gel yogurt was lower than what was observed for normal or controlled yogurts. In addition, we also observed that about 30 degrees Celsius, these disodium guanylated yogurt gels will melt. And also they have antimicrobial properties that does not affect the starter culture bacteria, but affects other spoilage and pathogenic microorganisms. So these are some of the characteristics that we found were very beneficial for using in the yogurt manufacture. So there are also other possible applications for this gel as well, which needs to be explored. So another dairy ingredient or use of dairy proteins as an ingredient in another industry is using dairy proteins like caseinate and whey protein isolates with milk, pea starch. So milk protein is in starch-based products used in bakery products, puddings, mousses, soups, and sauces. But if we think about starch that's sustainable, we can think about pea starch, which is a byproduct of pea protein production. And pea proteins are very high in demand because of the large commercial value for it, and also the customers or the consumers wanting more and more protein-based products. So this byproduct is low cost, and it has neutral taste, and it has high amylose content and strong gelling agent. So this pea starch can be utilized in many different products. So our study concentrated on incorporating milk protein at different concentrations with pea starch to understand the gelling properties. So if we look at the pea starch alone, if we heat it at 75 degrees Celsius, compared to pea starch with casein, heated at 75 degrees Celsius, you'll see that the granules were not hydrating as much as what you see in the pea starch alone. This means that the casein is inhibiting the hydration of these granules. And in turn, this also reduces the WPI, and casein incorporation along with pea starch also reduces the hardness of the gels that are formed using pea starch. So this could be a good application in different kinds of products, and we need to understand the functionality of these kind of dairy ingredients in a number of food products and industries, and that can open up many new markets as well. So another topic that I have worked with is research on milk protein-based delivery systems. So if you know what's the structure of the casein micelle, so it will look somewhat like this, with the different caseins incorporated in a very complex structure that forms structures of the size of even 100 nanometers to up to 500 nanometers in a broad range of sizes. So these polymorphic structures have different caseins incorporated in it, but also it has a lot of gaps and channels within it. So in these gaps and channels, there is possibility of incorporating many hydrophobic compounds and amphiphilic compounds, which the casein micelles that are loaded with these compounds can be used as delivery systems. So there are a number of ways of incorporating these molecules into the casein micelles. It can be by innate binding. We can chemically disrupt the casein micelles and then load the molecules within these casein micelles, or we can use mechanical disruption to disrupt the casein micelles and then bring it back together with the loaded molecules. So there's a lot of possibility of commercialization of loaded micelles, but we definitely need to compare the efficiencies and also evaluate the carbon footprint of these processes for different applications. So that would create, if we have a better system that can deliver sustainably different kinds of bioactive compounds, that will definitely help the drug delivery for a number of diseases and health conditions. So we further studied the molecular interactions and delivery mechanisms of casein micelles by incorporating polyphenols. So we used fruit polyphenols as well as tea polyphenols, and we figured out the green tea polyphenols bound to milk protein just by mixing with it. And we found that some of the higher molecular weight catechins, like the epigallocatechin galates, bound most to the milk proteins more than the low molecular weight epicatechins and epicatechin galates. So casein micelles can be utilized as vehicle for a number of functional compounds and to protect their bioactivity as well. So this needs to be explored much more to understand. However, we also need to develop a fundamental understanding of casein micelle structure. We only know that the kappa casein is arranged on the outside of the casein micelle, but we still don't know how the other caseins are arranged within the casein micelle. And also we don't know what kind of intermolecular and intramolecular binding mechanisms of the caseins occur, and with the different biomolecules that are incorporated, or bioactives that are incorporated in the casein micelles as well. So this is definitely a direction in which we should focus research on. So overall, I have discussed a number of different aspects, but that will all fit into this manufacturing process flow, where we have a number of raw materials, which can be modified raw materials, milk-based, dairy-based, or dairy-based modified raw materials as well. And that goes into processing technologies. It can be thermal, non-thermal, novel processes as well, and we need to study the process induced changes within these kind of processes to figure out what will be the impact on the product. And also much more research needs to be done for these novel processes and product development to be scaled up to be commercialized eventually. So the goal of my research is to develop optimized and sustainable dairy processes and ingredients, and also at the same time probe the fundamental science to understand and create better commercial solutions. So the vision is that the academia and the dairy industry can collaborate quite a bit in terms of teaching and research, and also co-innovation. These are some of the collaborations that I have established in different countries, and there's much more possibility for establishing more collaborations between the different countries and organizations, industry, as well as academic institutions. So some great teams that I worked with. And that's my presentation for today. Thank you for this opportunity, and I can take any questions that you may have.